Hello and welcome to Calculus 1, this special lecture on tangent lines. Tangent lines are part of every section of chapter 3, and it's one of the most important problems of Calculus 1 and calculus in general, because we learned that the slope of the tangent line measures the change, and that the derivative function is the function which generates slopes of tangent lines. So finding the tangent line becomes the central problem of calculus. So if you have any kind of a curve, red. If you, okay, there we go. If you have any kind of a curve, you can find a tangent line at any given point, right? It doesn't matter where you look, there is going to be a tangent line. So all these points have different x1, y1, have different coordinates. And observe that my line is not even a function, because now with the implicit differentiation we can find tangent lines of anything, function or a non-function, right? Because we can find those derivatives. The process of finding tangent line is straightforward. So process number 1, find the derivative. Number 2, m is equal to derivative computed at a. Number 3, use m and xy in y equal mx plus b, or y minus y1 equals to mx minus x1 to get the tangent line. It's a 3-step procedure. So find the tangent line. I'm just going to call that TL from now on. At x equals 3 for function f of x equals I don't know, 2x cubed minus x plus 1, whatever. So the procedure is to find the derivative, which is 6x squared minus 1, and then to find the slope you will compute the derivative at the value 3, because that's where we are interested, right? At 3, that's given to us, which will be 6 times 3 squared minus 1. 3 squared is 9, 6 times 9, 54, minus 1 is 53. We do not have the y value yet, so we have to calculate that, but y is simply f of 3. So that's going to be 2 times 3 cubed minus 3 plus 1, which is 27, 54 minus 2, 52. And now I have information on the line. M is 53 and the point is 3, 52. You can use either y equal mx plus b or the other formula. I'll do both, and then you pick whatever you like better. So if you're using y equal mx plus b, your y is 52, your m is 53, your x is 3, and plus b. So 52 is equal to 159 plus b, b equals to negative 107. And then you write your tangent line y equals, slope is 53, so 53x minus 107. And you're done. So if you use y equal mx plus b, that's the procedure. You have your x, you have your y, you have your m, you plug them in, you find b, and then at the end, to present the equation of the line, you say y equals mx plus b, you plug in m, you plug in b, and leave x and y alone, right? The other way is to use y minus y1 is equal to m times x minus x1. So y minus 52 is equal to 53 as a slope times x minus 3. And then you distribute and combine, right? So y is equal to 53x minus 159 plus 52 that you move from the right to obtain the same answer of 53x minus 107. So whatever method, you know, makes you smile, right? This is a math class. Your happiness is our primary concern. Whatever method from algebra makes you happy, use that method. You don't have to use both, right? But this is the procedure to find the tangent line. And now you go and say, okay, so what's different? Why is this in the entire chapter 3? Well, the function given over here can be the product rule, can be the chain rule, can be the quotient rule, can be combination of them, can be implicit, can be any of those. I did the example on the cheapest possible. Let's take a look at the tangent line problem from implicit differentiation section. You have them in a homework for every section. So they want to find the tangent line in problem 47. This is 3.8. In 47, they want to find the tangent line for x squared plus xy plus y squared is equal to 7 at the point 2, 1. What's the tangent line? So that's the problem. Well, step number 1, find the derivative, and you have to use implicit differentiation in this case. So the derivative of x squared plus xy plus y squared equals to 7. Derivative of x squared is 2x. And now we have the product rule. So copy the first, derivative of the second, plus copy the second. Derivative of the first is 1, so we don't have to write it. Plus 2y, again, dy dx, because we are looking for the derivative of y with respect to x, equal to 0. So this is our derivative. Now, here is the $1,000,000 step, which can significantly reduce your calculations and mistakes. You do not have to solve it for dy dx when you're doing the tangent line, because each dy dx becomes m if you plug in the points right away. So rather than solving dy dx equals everything else, plug in now 2, 1 to get 2 times 2 plus 2 times m plus 1 plus 2 times 1 times m equals to 0. See how cheap this is? It's much better to just compute this quickly rather than shovel algebra and make a mistake. Negative signs and all those things. So we have 4 plus 2m plus 1 plus 2m is equal to 0. That's 4m plus 5 equal to 0, from where m is quickly negative 5 over 4. So we have our slope, and we have our point, and we can quickly find the b, and we're done. So for implicit differentiation, you do not have to do all of those extra steps of shifting everything left and right and factoring and dividing. you can immediately plug in and reduce the number of steps by 4 or 5, which gives you time. Plus, again, less calculations, less errors. So now, y equal mx plus b. Y is 1. M is negative 5 quarters. X is 2 plus b. These two cancel. So 1 is equal to negative 5 halves plus b. And we add. So b is equal to 1 plus 5 halves, which is 7 halves. And our tangent line is y equals negative 5 quarters x plus 7 halves. And that's the answer. Every section in chapter 3 will have tangent line problems. The only thing that is different between section to section, problem to problem, is what type of the derivative are you going to take. Is it chain rule, product rule, basic, like whatever you have, you go and you take that derivative. The procedure for the tangent line is the same. Find the derivative with whatever section it applies, right? Whatever section applies for product rule is a product rule. And then when you find the derivative, calculate the slope by plugging in x. And then after that, you have the slope, you have the point, just find the line. So the tangent line problem will appear on every exam from this point on. Exam 2, exam 3, and the final. And then the tangent line will return as the tangent plane. Well, tangent line first and then tangent plane in Calc 3. So this is not something that you just, brush off right now. Yeah, it will also return in another lecture that we're going to have in chapter 4. So it will be, tangent line will be back. That's it. One more example? Okay, say no more. Let's go and find the quotient rule example, because we can. Quotient rule, tangent line. Problems 61 through 64. Find an equation with the line tangent to the curve at the given point. And they give us a few of these. So 62 has polynomials dividing, and 64 has exponential function divided by a polynomial. So what do we do? 62 or 64? 62? 62. This is in section 6. Section 3.4. So the function is y equals 2x squared divided by 3x minus 1. And the point they are giving us is at x equals 1. What's the tangent line? The first order of business is to calculate the derivative. So y prime is going to be, we have 3x minus 1 squared, then 3x minus 1 here, times the numerator derivative, so that's going to be 4x, minus 2x squared times the derivative of the denominator, which is 3. And again, I don't care about simplifying this now because I am plugging in x equals to 1 to find the slope. Plug in x equals 1. So m equals, so as soon as you plug in x, your derivative, whether it's a y prime or dy dx, turns into m. So now we have plugging in 1. So it's going to be 3 times 1 minus 1 times 4 times 1 minus 2 times 1 squared times 3 divided by 3 times 1 minus 1 squared. 3 minus 1 is 2, so we have 2 times 4 minus 2 times 3 divided by 2 minus 1 squared. So 8 minus 6 is 2 divided by 1 squared, which is 1. So the slope is 2. So we have the slope. Now to find the y value, we plug in 1 in original function. So that's 2 times 1 squared over 3 times 1 minus 1, which is 2 divided by 2, which is 1. And now we have everything we need to calculate our line, because slope is 2 and the point is 1, 1. Y equal mx plus b. Y is 1, slope is 2, the other one is 1 plus b, so b is negative 1, and our tangent line is y equals 2x minus 1. Now it's important to understand that this is the tangent line only at, let me write that in blood, only at x equals to 1. If you change x equals to 1, immediately the entire thing changes, because, right, you will not be plugging in 1 any longer. This tangent line, the linear line, the tangent line in the bottom, is as 2x minus 1, is only the tangent line at x equals to 1. If you change this, then the slope will change and the calculations will change and everything changes and you get a different line. Yes?
Wouldn't m be 2 over 4? Just like you can 3 minus 1 2 squared and 2 over 4, so it's 1 half.
2 minus 1 is 1.
No, but then you put 3 minus 1 is
Oh, yes. Yep. 3 minus 1 is 2 and 2 squared is 4, and that changes everything. Great. So the slope is 1 half. Slope is 1 half. Slope is 1 half. And then 1 minus 1 half is 1 half. So this is plus 1 half. All right. Fine, thank you. I have no clue why I had 2 minus 1 over here. It's just, should be 2 squared. There we go. Woohoo! Those are the tangent lines. So get your derivative, plug in the x value to get the slope, then plug in x value in the original function to get the y. You have x, y, and m. Calculate your b, and just write down what the line is. Over and out. Bye.